Hey there, Mr. Thrasher here. I am going over page 13, this conservation of momentum. It's a tough paper. There are some difficult problems. Let's go through and hopefully you can listen to my explanation as I answer these. And of course, you can hit pause, you can rewind, you can re-listen. And if you have any questions outstanding, you are free to email me or come chat with me. All right? So I'm going to scroll down. We already have our notes done. For this first part, we were writing down the momentums based on the information that's given in the problem. So I got my little PDF annotator here. Sometimes it's a little funky, but hopefully it works out. This first problem, okay, the stationary bomb, it tells us I have a momentum of 0. Remember, conservation of momentum says whatever momentum I have in the beginning is the momentum I have in the end. So if I started with 0 momentum, that must mean I finish with 0 total. I get the diagrams are a little weird at first, but it's total because look what they're doing right here. They're adding, they're finding the total. So that's how I know that this spot here is asking about the total momentum. So I started with 0, I have to end with 0. But they give me more information. This bomb is moving to the left with a momentum of -10. But remember, the total momentum needs to be 0. So what do I place right here so that the total momentum is 0? It has to be +10. I'm not going to write down the units because this first part is pretty quick. Because -10 plus 10 is 0. How did I know it was 0? Because that was the total momentum before. Momentum is conserved. It stays the same. Let's go to the next problem. This piece is moving with a momentum of 10. This piece is not moving. It has a momentum of 0. What's the total? Literally, add them up. Add up the two pieces. What's the total momentum? 10 plus 0 is 10. So the total momentum in the beginning is 10. What does the total momentum in the end have to be? Well, momentum is conserved. Whatever I have in the beginning is what I have at the end. I started with 10 in total. You're going to hear that word a lot from me. So I must end with 10. Bam, number 2 is done. Let's scroll down to number 3. Now number 3, again, this piece is moving with a momentum of 10. This piece right here has a momentum of 0. What's the total? It's 10. 10 plus 0 is 10. This is the total momentum I'm ending with. This is my P initial. What does the total momentum, P final, have to be? It's the same thing. Momentum is conserved. So this ball and this ball have to add up to be a total momentum of 10. This first one, it tells me it has a momentum of 0. So what does this one have to be in order to have a total momentum of 10? Yeah, it has to be 10. Bam, keep going. Number 4. All right, this one gets a little trickier, but just a little bit. Now the bomb was moving. It's like I threw a grenade. So it has some momentum. This is the momentum before. This is the momentum before. What's the momentum after? It has to be 10. It has to be the same thing. Now this piece is moving, and it has momentum to the left of -10. Remember, negative just means it's going to the left. So it has momentum of -10. The total needs to be 10. So what number do I have to add? That's 0. What number do I have to add to -10 to get +10? Oh, careful. Not 10. 20. This is 20 because 20 combined added to -10 gives me +10. So that's the right answer right there. All right. Few more. All right. Now things are colliding. They're sticking together, but momentum is still conserved. For this one, this piece is positive. So piece 1 is moving to the right, like that. There's my action lines. It's moving to the right. Piece 2, I don't know. And the total, I don't know. Well, look over here. Now I'm looking at the end. A little tougher. It says the momentum is positive. Positive meaning it's flying to the right of 4. That's the final momentum. Well, if I know the final momentum, momentum's conserved. The final is the initial in total. So the final is 4. The total in the beginning must be 4. So that's how I know now if this is 10, this number right here must, when added to 10, equal 4. You might have to whip out your calculator for these, but I'm an old man. I know after enough time that this number must be -6. -6 added to 10 gives me +4. That's the answer to number 5. Number 6, keep going. Okay, this piece here has a momentum of +10. That means it's moving to the right. This piece here has a total momentum, or it has a momentum of -13. Negative meaning it's moving to the left. What's the total? What's 10 plus -13? It's -3. Use your calculator if you need to. If that's the momentum in the end, the momentum in the beginning must be the same because momentum in total is conserved. Okay. Now this piece here, piece 1, has a momentum now after the two bounced off each other, has a momentum of -8, meaning it's going to the left. This piece here, I don't know. What is its momentum? The total must be -3. So what number, when added to -8, gives you -3? It ends up being +5. +5 plus -8 gives you -3. How did I know it had to be -3? Because that was the total before. All right, number 7 and 8. These are the trickier ones. What's tough about 7 and 8 is now it's asking about the velocity. We were just using momentum before. You can figure out the velocity using our momentum equation. If I know the mass and I know the momentum, I can figure out the velocity. So here I have a kid that's running. They jump onto the cart, and then, I don't know, what's your action word? Jump, okay? And then the wagon and kid are moving over to the right. So, okay, I can find the velocity if I know the mass and if I know the momentum. Do I know the mass of the kid in the cart? I do. The mass of the kid is here. The mass of the cart is here. Now they're together. So it just means I would add them together. It's very logical. 40 plus 10, if you need a calculator, go ahead. But that's 50 kilograms. I'm halfway there. I can find the velocity, what I'm looking for, knowing the mass, if I can figure out the momentum. Am I told the momentum here? No, I'm not told the momentum. Uh-oh, yikes. But I can figure out the momentum here. And remember, whatever the momentum is in the beginning, by conservation of momentum, that's the momentum at the end. So in the beginning, let's find the momentum of this piece. Remember, momentum is mass times velocity. So the mass is 40, the velocity is 5. So for this piece, P1, 40 times 5, that's 200. If you need a calculator, go for it. Is the cart moving? Uh-oh, no. The cart has 0 momentum. It's just like all the problems we saw before where the thing wasn't moving. If you're not moving, you have no velocity, you have no momentum. So what's the total momentum before? It's 200. So what does the total momentum after have to be? It has to be 200 because conservation of momentum. So now I know this is 200 equals 50 times v. How do I solve for v? I divide both sides by 50. We're doing this kind of algebra all year. You've been seeing it for weeks now. Hopefully it's getting more familiar. Okay, 50 divided by 50, that cancels, so I'm left with v equals 200 divided by 50. That is 4 meters per second. That's the answer for number 7. Okay, let's try number 8. 7 and 8 are both toughies. Again, for number 8, it's asking for the velocity. So again, if I know the momentum and if I know the mass, I could solve for the velocity of this bomb. Now the bomb starts as one piece and then it breaks into these two pieces. The diagram could have been a little more clear, but if this piece is 4 and this piece is 3, that means in total it's 7, right? Okay, it just broke into 2 smaller chunks, but the total mass should be 7 kilograms. So if I know the mass, okay, P equals 7 times V. If I know the momentum, I'm in business. Oh, I don't know the momentum. But if I can figure out the momentum after, then by conservation, it must be the same thing. So can I find the momentum before? Absolutely. Let's find the momentum of this piece. Remember, momentum is mass times velocity. So it's this mass times this velocity. So that's going to be 4 times, don't forget that negative. Remember, negatives are important. That's negative 20. What's the momentum of piece 2? Ooh, it's 3, the mass, times the velocity, times 12. That's 36. So what's the total momentum? Negative 20 plus 36, that's positive 16. That's the total momentum after. So what does the total momentum in the beginning have to be? By conservation, it's the same thing. So this right here is 16 equals 7 multiplied by v. Solve for v. 16 divided by 7. I hate fractions. Get your answer in a decimal. You'll always make me happy. In your calculator, 16 divided by 7, punch that in. I get about 2.28. That's meters per second. That's the velocity of the bomb. All right, those are the tougher problems right there. Now, I've jumped ahead a little bit. Now on to number 15. Here's some more math questions. To be honest, you could say that I made maybe a less than crystal clear setup right here, but it was me trying to show you these steps. These are the toughest problems you might come across, and I wanted to kind of show you step by step by step. To be honest, we haven't done this before, so maybe it was more confusing than not, and I'll put that on myself. My apologies. But here's the idea. It's using the same idea as before. Whatever the momentum is in total in the beginning is equal to whatever the momentum is at the end in total. So if there's two pieces, I would take the momentum of piece 1 and add that to the momentum of piece 2. That must be equal to the momentum of piece 1 and the momentum of piece 2 after they collide. So what's the underlying idea? The momentum before and after is the same. All right, well, this piece has some momentum, theoretically. This piece has some momentum. In the beginning, though, it tells me that this billiard ball is at rest. So if it starts at rest, its velocity is 0. That's why I automatically plugged in a 0. If you have no velocity, you have no momentum. But this steel ball, it does have momentum. It tells us in the problem it has a mass of 0.8. So right here, the mass of the steel ball times its velocity. So the mass is 0.8. The velocity, it tells me, is 1.3. Okay, so on the left-hand side of the equation, 0.8 times 1.3 plus 0, but, I can kind of just ignore that, is equal to, after they collide, after the clack, it says in the problem that the steel ball is at rest. So does it have any momentum? No, it's not moving. But now the billiard ball is moving. The billiard ball, with its mass of 0.5, is moving, and I'm trying to find that velocity. That's my unknown. So here's what I have. If I rewrite it, I have 0.8, multiplied by 1.3 equals, this kind of is ignored, 0.5 times the velocity. And you can do this in your calculator. Put in 0.8 multiplied by 1.3, and then you've got to divide by 0.5. So your overall answer, if you do the math right, is 2.08 meters per second. How did I do that? I know the total momentum before and after are equal. So I just calculated the momentum of the first and second object before they collided. I calculated the momentum of the first and second object after they collided, and I set them equal to each other. And that's how you're able to get an expression, how you get an equation. All right, two more. You might have seen my little head move because I wanted to get it out of the way. Another problem using the idea of conservation of momentum and doing some math. So, okay, I'm trying to find the velocity of this boy in the little bumper car after the collision. They hit and they bounce off each other. What do I know? I know that momentum is conserved, so the initial momentum is equal to the final momentum. So if I can figure out the momentum of the first object, the boy, and I add it to the momentum of the second object, the girl in the bumper car, that must be equal to the boy's momentum after and the girl's momentum after. The boy's momentum, it tells me that the boy's bumper car is 30 kilograms in total, moving to the right. That's where these numbers came from right here. What information do I know about the girl and her bumper car? Well, the mass is 15, so I'll plug in 15 there. The velocity is 4 meters per second. And remember, negatives are important. You could put the negative here, or if you put the negative right here, that's okay. But this should be a minus ultimately, all right? After they collide, it says the boy is moving to the right at some unknown speed, and there's that mass of the boy, still 30. And we know that the girl's bumper car, is moving to the right, so that's positive 1. And the mass hasn't changed, that's 15. Okay. Again, maybe you criticize how I structure this. That's maybe a valid critique. But the idea was to help you see how I'm kind of looking at the momentums before and the momentums after, how I'm adding them before and after, and then how I'm setting them equal to each other. So right here, if I just do a little work in the margins, 30 times 3, that's going to be 90, plus negative 60. So what does that equal? That equals 30. So that's what this top part is right here. But you can't forget this. This is 15. You'd have to, in your algebra, subtract that. Because right now I have 30, what I just found, equals 30v1 plus 15. So I got to swing this 15 over. So 30 minus 15 is 15, okay? So that means I have ultimately 15 equals 30v1. Divide both sides by 30, I get 0.5 meters per second. Okay, again, maybe I could have structured this a little differently, but that's how you do the math. Again, I add up the momentums before and after, I add them up, and I set them equal to each other. All right? Last problem. So on this last one, again, it's a collision. Again, I'm going to add up the momentums, set them equal to each other, but now they're sticking together. So what does the initial momentum in total equal? It's the final momentum in total. Here's the clay blob's momentum. Here's the steel ball or the bowling ball's momentum. And then after they stick together, if they're stuck together, they're just kind of like one bigger object. That's what this is meant to show you. It's a little weird, but just add up their masses because now they're together. Okay, so what's the mass and velocity of the blob of Play-Doh? Well, the mass is 0.5 and the velocity is 9. So the mass, 0.5, and the velocity is 9. The bowling ball, while it has mass, what is the velocity of that bowling ball in the beginning? It's nothing. It's at rest. So I'm just going to slap down a 0. So this just kind of goes away. But now they're connected. So I need the mass of the two pieces. So the mass of the ball of Play-Doh is 0.5. The mass of the bowling ball is right here, 7. So 0.5 plus 7. All right, okay. So now, again, I'll go in my margins. 0.5 times 9, that's the same as me writing 4.5 equals, what's 7 plus 0.5? 7.5 times v. So you should know what to do. Divide both sides by 7.5. 4.5 divided by 7.5, I get an answer of about 0.6 meters per second. Again, notice, I'm always doing the same thing. The total momentum in the beginning is the total momentum in the end. I write out the momentum of the objects before and after. I plug in and I solve for my variable. Well, these are the toughest of the math problems, okay? That's it. Hopefully this video was a little helpful seeing how I answered some of those math problems. Thanks a lot for watching. If you have any questions, be sure to email me or come see me during class time, okay? Take it easy.